So we have steam, which is the working fluid in an ideal Rankine cycle. Okay, so ideal Rankine cycle simply means that the isentropic efficiency within the turbine expansion is 100%. So the process 1 to 2 and 3 to 4 is isentropic. Same as the process 5 to 6. Okay, 5 to 6 happens in the pump. 1 to 2 happens in the first turbine stage. 3 to 4 happens in the second turbine stage. Okay, so these are all isentropic processes. Now, what else is given? Okay, it's an ideal Rankine cycle with superheat and reheat. Okay, that's what we see from the schematic as well. There's some reheat as well, right? And the steam enters the first turbine stage at 80 bar and 480 degrees Celsius. This is exactly the same temperature we had in the case for a simple Rankine cycle. Okay, now it enters at these conditions, expands to 7 bar. So the steam enters at 80 bar 480 degrees Celsius at state 1, expands till 7 bar. This is 7 bar, right? Reach to state 2, and then at state 2 we reheat it to 440 degrees Celsius. So it's reheated from 2 to 3, and T3 is 440 degrees Celsius. The pressure is same as 7 bar, and at this condition it enters the second stage turbine. Now, in the second stage turbine, it expands all the way down to condenser pressure, and the condenser pressure is pretty small, 0.08 bar. Okay, it's much smaller than the atmospheric pressure. Now, the net power output for this cycle is 100 megawatt, and the mass flow rate of steam is given as 2.363 into 10 per 5 kilogram per hour. Now, for the information given here, we need to calculate the thermal efficiency of the cycle and also the rate at which heat is being rejected. So Q dot out from the condenser. Okay, so these are the two things that we need to do. And before I go ahead and talk about the thermal efficiency and other stuff, I just want you to have a quick look at the cycle. Okay, and be very clear in your mind what all is happening. So let's start with process 1. So 1 to 2 is the expansion happening within turbine 1. All right. So we have the temperature and the pressure for state 1. 2 to 3 is constant pressure heat addition. Okay, so P2 is equal to P3. And T3 has been given to us. Now 3 to 4 is again the expansion happening within the second stage turbine. Okay, so it's undergoing isentropic expansion. S4 is equal to S3. Okay, because it's an ideal cycle. Now 4 to 5 is what happens is the heat rejection within the condenser. Now this heat rejection process is again constant pressure. So P4 is equal to P5. From 5 to 6, we're sending it to the pump. The role of the pump is to pressurize this the incoming water from 0.08 bar to 80 bar. Okay, talking about a huge pressure increase, right? So that happens from 5 to 6. Now at 6, again we send it to the boiler. Okay, and it undergoes heat addition. So 6 to 1 is basically heat addition. Now this heat addition again occurs at constant pressure. So P6 is equal to P1. All right. Now between 1 to 2 and 3 to 4, we had this other heat addition, which was again a constant pressure. So if you look at this entire cycle, every process other than the expansion and the compression within the pump happens at constant pressure, right? So it gives you information about the states already. So with this information known, let's go ahead and tackle the first part, the thermal efficiency of the cycle. Okay, so if you want to determine the thermal efficiency of the cycle, which is basically the net work output divided by heat input, well, we need to get some enthalpies, right? Without that, it's not really without that, it's not possible to determine the thermal efficiency. So here, although we know the temperatures and the pressures at some states, we have no clue about the enthalpies. So that's the first thing that you got to do. Okay, so the way we determine the enthalpies is very similar to what we did earlier for the simple Rankine cycle. So I'm not going to spend a lot of time onto that. I'm going to go over it very quickly. If you have any questions, please stop me and we'll discuss that. So let's start with determining the properties at all the states. State 1, we have been provided the pressure and the temperature. The pressure is 8 MPa or 80 bar, and the temperature is 480 degrees Celsius. This was known, so it's just a matter of going to the superheated vapor tables, picking up the value of H1. That's it. Okay. Now we also determine S1 or the entropy at state 1 because we want to locate state 2. For state 2, we know the pressure, it's 0.7 MPa or 7 bar, but we don't know anything else. Now we can make use of the fact that it's an isentropic process, right? And which basically means that S1 is equal to S2, and then use this to determine the quality at state 2. Okay, so we go to the pressure tables, get the values of SF and SG at the pressure of 7 bar, and S2 is equal to S1. So that's the value that we already have. We plug it into this equation and calculate X2. As you can see, X2 is almost close to 1, which indicates that it's almost saturated vapor, right? It's pretty close to being a saturated vapor. Now, once you have X2, it's very straightforward to go and determine H2. All right, H2 is simply HF plus X2 times HFG. And these values are again given in the property tables for given pressure. And what pressure do we look out for? We're looking for pressure of 7 bar. Okay, so you get the values of HF and HFG, and we plug in the numbers here, and you get H2 of 2741.8. So H1 and H2 are determined now. H3 and H4, the way we determine them is exactly the same. Okay, the state 3 is again it's superheated vapor. We know the pressure, right? It's 7 bar, and the temperature has been given as 440 degrees Celsius. So using this information, you pick up the values from the table. Again, we don't know much about state 4 except the fact that 3 to 4 is an isentropic process. So S3 is equal to S4, right? And we know the pressure at state 4. So once you determine S3, we also go ahead and determine S3 from the property tables and use it to calculate X4, just like we did X2. Okay, once you have X4, then it's just a matter of plugging in the numbers and calculating the enthalpy at state 4, which is actually what we need, right? It's simply be equal to HF plus X4 times HFG. Now these values, HF and HFG, are at 0.08 bar, right? Are at the condenser pressure. So once you plug them in, this is what we get as the value for H4. Now there's something important I want you to point out here, and I want you to look at this value of X4. See, this X4 is pretty high. It's 0.9382. Again, indicating that we're having a majority vapor, very little liquid droplets. Okay, and if you recall, we always spoke about trying to increase the value of X so that the turbine blades do not get damaged quickly. And if you recall the value of X we got when we did not have the superheat or the reheat, the X value was somewhere around 0.7. So you can see that implementing superheat and reheat has allowed us to increase X value or the mixture quality to a value which is very good, to a situation where we have very little liquid droplets. And this is exactly what we need. And the excellent situation about this is the fact that we did this at no cost, right? We are able to achieve higher efficiencies as well as higher qualities. So this is a win-win situation, except the fact that you have to certainly put in some investment to purchase one more turbine and do some piping to send it to the reheater, which makes economic sense and pays off. That's why this modification is extremely common. Okay. Now we had all the 4 enthalpies that we need. We need 2 more enthalpies, H5 and H6. H5 is actually very easy to determine, right? H5 is simply enthalpy at state 5 is simply HF at this pressure, at the condenser pressure, right? And this is something that you already determined when you're looking at H4. Okay, so in the formula for H4, this number is H5, and that is what it was given. This is HF, and this is basically H5 because 4 and 5 are at the same pressures. Okay, so we know H5. Now determining H6 is again straightforward. We already discussed this before, and we make use of the reversible work input formula, which is specific volume at 5 times delta P, to determine the work input. All right. So this is H5 plus specific volume. You got to be careful about dividing by 1000. All right, and this is typically happens when it's written for VF. So as long as you take care of that, this is pretty straightforward. Okay, and H6 comes out to be 181.94. Now this value is something very similar to what we discussed before, and calculation of H6 is something, or calculating the enthalpy at the exit of the pump is something that I like to give. So make sure you understand this and look for it. Okay. So with this, we have all the enthalpies calculated. We have 6 states, we have 6 enthalpies. Now the question is, how do we go ahead and determine the efficiency? All right. So efficiency is, as I said, network output by Q1. Here we need to consider the fact that the work output is happening at 2 different turbines, from 1 to 2 and from 3 to 4. All right. And at the same time, the heat input is happening at 2 different steps, from 6 to 1. All right. And also from 2 to 3. So we need to take both of this into consideration. And as long as you take both of this into consideration, you're going to solve this problem correctly. There's no other trick in here. There's no other point where you can make a mistake. So now let's look at the net power output within the cycle. Okay, so it's the work done in turbine 1 plus work output in turbine 2 minus the pump work, which is the usual stuff. Okay, now the work done in turbine 1 is equal to H1 minus H2, right? The inlet of turbine minus exit of the turbine. Same way, work done in turbine 2 is H3 minus H4, the enthalpy at the inlet of the turbine minus enthalpy at the exit of the turbine. The pump work is H6 minus H5. Okay, why is it the opposite? Simply because we are actually providing work input. So enthalpy at 6 is greater than enthalpy at 5 because of the work input we provided. Now, how did we get this? Well, these are all from energy balance. If you have a confusion, start with energy balance and you will be able to get them very easily. Now, what about the heat input? Okay, so heat input is happening at 2 different points, in the boiler and in the reheater. So the heat input is divided by the mass flow rate is simply equal to H1 minus H6, which is what happens here, right, during the boiler, and then H3 minus H2. Okay, so H3 minus H2. So this is what happens at the in the reheater. So this is all what we need. Okay, we have all the enthalpies. We know how to calculate the work outputs and the heat inputs, and we are considering everything that is happening here, both the heat input in the boiler as well as the reheater, the work output in the turbine 1 and turbine 2. Once you do this, it's a matter of plugging in these enthalpies and solving for it. There's nothing else in here. All right, any questions? Okay, so then let's calculate the thermal efficiency by just plugging in the enthalpies that we wrote here. Okay, so once you plug in the numbers, these are the different numbers that we had for H1 to H6, as we just found. Once you plug in all those numbers, what we get is we get an efficiency of 40%, 40.3% to be more specific. All right, and now, as I mentioned before, the state 1, or the temperature and pressure at state 1, is exactly same as the one that we had for the simple Rankine cycle, and the condenser pressure is also the same. All right, so if you sort of just compare this one with the simple Rankine cycle, we see that in the simple Rankine cycle, where we did not have superheat and reheat, the efficiency was 37%. Now, by going towards superheat and reheat, or by making the simple modifications of superheating and reheating, we're able to increase the efficiency by about 3%. Okay, so this is a significant amount, and this is the whole reason why we make these 2 modifications, apart from the fact that we also get good quality at state 4. Okay, so this is something which is common in all practical power systems that you're going to see, right? All of them have superheat and reheat stages. So that's the first part about calculation of thermal efficiency. Now we also have to calculate the rate of heat transfer, Q dot out, from the condensing steam as it passes through the condenser. So as the steam passes through the condenser, it has to reject some amount of heat. The question is, how much is that? Okay, how much does it have to reject? Now we were provided the network output of the cycle. It was 100 megawatt. Okay. Now we need to calculate the Q dot out, and we also know the efficiency. Before we go ahead and calculate, can anyone make a guess what the value would be? Would Q out be, would it be greater than 100 megawatt, or would you expect it to be smaller than 100 megawatt? 100 megawatt is the uh, network output from the cycle.
I think less.
Okay. What about others?
Greater than.
Okay. Any reason why you think it'll be greater than?
Because the efficiency is lower than 50%.
Yes, perfect. Makes sense. So you see, efficiency is simply network output by Qn, right? And the heat that you're providing it, it's either going to produce a network output or it's being rejected. Okay, so Qn is net work output plus Q out. Since we know that this ratio is less than 50%, it's 40%. So we know that 60% of the heat input is going for heat rejection. Okay, so it basically means that the Q out should be greater than 100 megawatt, considering that it needs to be greater than the work output, network output. Okay, so we would expect it to be greater than 100 megawatt. Now there are several ways of calculating this Q out here. You could make use of the fact that we know the efficiency, we know the network the network output, and calculate Q out using that information. Or you could also just do a simple energy balance on the condenser. Okay, so if you look at the condenser, I mean, if you just write the energy balance, it's a steady state, steady flow system, just like any other component in there. And there's no Qn, there's no work in. The only way energy is entering it is through enthalpy, right? It's with the mass flow rate, so it's m dot h4. And then on the other side, yes, there is some amount of Q out. There is no work output, plus it's leaving at state 5. So Qn is 0, work in is 0, work out is 0. So here you just have m dot h4 is equal to Q dot out plus m dot h5, or Q dot out is equal to m dot times h4, and I send this h5 to the other side, h4 minus h5. Okay, so this is what you have. We have the mass flow rate already given in the question. H4 and H5 are what we calculated in already. Okay, so you plug in the numbers, and this is what we get: 148 megawatt.